So we're getting down to the wire here. We've got half of this 10.3 lesson left to kind of look at. And then next week will mostly be just work days for you guys to make sure that you have everything in. You're all caught up before the final exam, which is 2 weeks from now. So um, not too much left to cover for us. Before we start taking a look at 10.3, though, are there any major questions with anything? So, anything about deadlines coming up, anything regarding lessons 10.1, 10.2, the start of 10.3. Like I said, we hadn't finished 10.3. Hopefully, we'll do that today, but any questions up to this point? All right, I'll take that silence as a no. So I'm just going to kind of fast forward through the PowerPoint so far of what we looked at in Tuesday's class as a quick reminder. So there are three different ways that we can actually find our limits. We can do them graphically, numerically, or algebraically. We tend to focus on the graphic side of things and the algebraic side of things. We can use the numeric or that table once in a while, but most of the time we're looking at graphs or we're trying to simplify to do and use substitution to solve it algebraically. We talked about all the different properties that we can apply with our limits. So if it's easier to break our function into different pieces and maybe add or subtract or multiply or even divide, we can do that using these properties of limits right here. We took a look at how we could use those properties and find these limits here by using substitution and kind of focusing on that algebraic approach a little bit. And then we stopped and we reached this one-sided and two-sided limit topic. So this is where we're going to pick up today. So when we take a look at a limit, generally we're trying to find the limit as it goes to a certain value. So we'll see that written as the limit as x goes to c, where c is some integer. Now, if you're taking a look at the graph, we have to actually verify that the limit as that x goes to that number is the same from the left as it is from the right-hand side of the graph. So we can break it into two separate pieces. We can look at the left-hand limit and we can take a look at the right-hand limit. And if the left-hand limit is the same as the right-hand limit, then we know that that will be the limit as x goes to that number as a whole. However, if those limits differ, so the left-hand limit is different from the right-hand limit, then the limit as a whole does not exist. So we're going to actually run into that concept today where maybe the limit doesn't exist because you have a break or a gap or an asymptote or something's happening at that spot. So that's what we're going to be taking a look at in the last kind of half of this lesson is, does the limit exist? And if it doesn't, what maybe is happening there? All right, some notation to be on the lookout for. When we talk about the left-handed limits, you'll see x as approaching the number c here. But if you see this little minus sign in the exponent area, that means we're taking a look at what the limit is from the left-hand side. So we're going to follow the graph in from the left to see what it's approaching as it gets closer to that number. If there's a little plus sign here, in the exponent area after that number, that means we're looking from the right-hand side of the graph. So we're going to follow that graph in from the right-hand side to see what it's getting closer to as it approaches that number. So let's go ahead and take a look at an example down below here. We want to find the left-hand limit and the right-hand limit as x goes to 2 of this function. And we've actually got kind of two different functions that are going to make up our graph. So let's start from the left-hand side. So from the left-hand side, we're really interested in what this left piece of our graph is doing. So coming in from the left, what is that getting closer to as we approach the number 2? So we got to figure out what value is that getting closer to on the y-axis as we come into 2 from the left. Yeah, it looks like it's approaching the number 3. Now we can confirm that using our functions over here. Right, so we can actually confirm that that y value will be 3 by looking at which piece of the function we should focus on. If we're coming in from the left, those are x values that are smaller than 2. So 0, 1, -1. All of those fit into this top piece right here. So if we substitute in 2 into this top function, let's see what the output is going to be. Hopefully it's our 3 that we think we're seeing in the graph. But let's substitute in and see what that actually simplifies to real fast. So because that negative is on the outside of the x squared, it will remain a -4 there. Does that simplify to that 3 value that we thought we saw with the graph? It did. Good. So we would say that the limit as x goes to 2 from the left-hand side equals 3. Let's see what we get from the right-hand side. Now we're interested in what's our value approaching as we go closer to 2 from the right-hand side of our graph. So that would be that piece right there. What are we getting closer to from the right-hand side? So what does it look like it's approaching? It looks like it's approaching 1, right? If I were to come over here. But algebraically, we can confirm that if we use the right function in our piecewise graph over here. So from the right-hand side, those are values larger than 2. So 3, 4, 5, 6, 7. We want to use the second function right here. So if I substitute 2 into that second function, do I in fact get a 1 as my output? And yeah, we do. We can see that one pretty quickly. So we're going to say the limit as x goes to 2 from the right-hand side equals a +1. Now because these two limits are different, the limit from the left-hand side is different than the limit from the right-hand side, we can then conclude that the limit as x goes to 2 as a whole does not exist. And the reason for that is because it's approaching different values as you hone in to that x equals 2 value. Right? You're approaching a +1 from one side and you're approaching a +3 from the other. So as a whole, if you were to take that both together, it does not exist because it's going to two different places. Okay. Questions with how we found the left-hand limit, the right-hand limit, and then we were able to use that to determine what the limit as the whole was. All right, the only way to get better at this is to practice. So we're going to go ahead and take a look at a few more here. It says let f of x be these two functions here. So if x does not equal 3, you can use this top function. If x does equal 3, it will be this bottom one. It says find the limit as x goes to 3 of f of x and prove that f is discontinuous at x equaling 3. All right, so how do you think we're going to prove that it's discontinuous at x equaling 3? Something's got to be happening at that point for it to not exist, right? So if it's discontinuous, there's got to be a hole or a huge gap or something happening at that spot for it not to be, for there not to be a limit there. So what exactly is happening here? Well, how about we check it out? What is the limit as x goes to 3 from the left-hand side? 6. Yeah, and we can prove that algebraically by taking a look at the function right here. I would try to break that apart or kind of simplify it, so to speak, by factoring. We have the difference of squares in the numerator there. If I were to use substitution right off the bat, I get 0 in the denominator. So most of the time, I would say probably 99.9% of the time, we take that function and we try to reduce it or simplify it. And then we'll use substitution into that. I notice the x minus 3's can cancel. So now that I've simplified that, I can go ahead and, oopsie, that should be a plus sign there. I can go ahead and use my direct substitution and plug in 3 for x. 3 plus 3 equals 6. So we're going to see that from the left-hand side. So 3 from the left equals 6. What is the limit as x goes to 3 from the right-hand side? It's also 6. Yeah, because we're still using this top part. So if we didn't have this second piece of information given here, if this was not part of the problem at all, we could conclude that the limit as x goes to 3 is 6. However, they throw in this extra piece here, and they say the limit as x is 3 is 2. Or the value when x equals 3 is 2. So because 2 does not equal 6, we know that f is discontinuous then. Okay, so because this value right here did not equal what we got from the left and the right hand sides, that's enough to say that f is now discontinuous. Which we could kind of see in the graph already, right? Because we saw this kind of open hole, but then the filled in hole was way lower than that. So we knew that there was going to be a problem area there and that the limit probably does not exist when x goes to 3 because we do have that gap there. Okay. Questions with example 5 at all? All right, let's take a look at the integer function here, the greatest integer function. It almost looks like a step function that's occurring. Let's see if we can answer these parts A, B, and C. You can actually get this graph on the graphing calculator. I think it's in the math portion somewhere. Yep. So if you need to graph this on your own graphing calculator, you would go to your y equals. And then if you hit the math button over here, if I hit math, and I scroll over to the number category on the top, so use my arrow, scroll over, you can see that int function is number 5. So if you hit that and then put your x value in, you can replicate that graph that you see on the screen here. You might have to do that for homework or the Unit 10 test. So knowing how to replicate that on your own might be a good idea to just double check right now that you can get that. And when you hit the graph, you can see that nice, wonderful kind of step function occurring. It looks like almost a staircase, so to speak. All right, let's see if we can answer the questions that are pertaining to this right here in part A. The limit as x goes to 3 from the left. So here's that 3 value that's in question. This is what we are trying to look at, what our graph approaches from both sides. So from the left-hand side, I'm interested in it going this way. What is the y value of that step there as the limit as x goes to 3 from the left? That's a 2, yeah. So the limit as x goes to 3 from the left is 2. Now what about if it's coming to 3 from the right-hand side? So from the right-hand side, we actually are using a different step, right? We're up at this piece now. What is the limit as x goes to 3 from the right-hand side? All right, so what can we conclude about the limit as x going to 3 as a whole? Is there a limit or does it not exist? It's a DNE. Yep, does not exist because 2 is not the same as 3. Good, so 2 is not the same as 3, so as a whole, it does not exist. Okay, next let's just take a look here as x goes to infinity or negative infinity. So in the past, we've always had x approaching a certain numerical value. What happens if we generalize it now? And what happens if we say x goes to infinity, or if x goes to negative infinity? Well, there's a couple of examples that can happen. You can still have it approaching a numerical value, like the limit may actually be a constant or integer value of some sort. Or we can say that it's increasing without bound or decreasing without bound. So sometimes now we actually have the option of our limit equaling infinity or the limit equaling negative infinity as well. Let's take a look here and see what they have in example 7. Let f of x equal this function sine of x over x. Find the limit as x goes to infinity and find the limit as x goes to negative infinity of the function. So the first thing that they're going to do is just look at that graphical representation. That's what I would do as well, because when you start plugging infinity in for x, it becomes very hard to simplify with that substitution process. So most of the time when we're dealing with x approaching infinity or negative infinity, we rely on the graphical aspect to help us find those limits. All right, so as x goes to infinity, we're interested in what's happening to our graph. What is it approaching as x gets larger and larger and larger? What do you think? Is it approaching a certain value? Yeah, I would say it's getting closer to that 0. Maybe it's oscillating up and down between it, but eventually, hopefully, I think it's going to kind of turn into almost a straight line on 0. So I would say that the limit as x goes to infinity equals 0. What about negative infinity? So negative infinity is that negative direction. Yeah, same thing is kind of happening over here, right? It looks like it's approaching 0. If both of those are approaching 0, can we conclude that the limit, oh, actually we wouldn't really have a full limit there because negative infinity and positive infinity are different. I was thinking from the left-hand side and the right-hand side. My bad. So we do have to leave these actually separated and can't conclude anything beyond that. So we actually just wrap this up from here. Questions with how we determine the limit as x is getting extremely big or if x is getting extremely small. So nothing too challenging there, just knowing that the graphical approach is probably the easiest to identify limits as x goes to infinity or negative infinity. Okay, let's take a look at this next example then. Yeah, so if you need to do graphing on the homework, I would just graph this function. So just grab your graphing calculator and all you would have to do is type in the function for f of x. So it's nothing extraordinarily difficult there. Just go into your y equals and you would do sine of x divided by x. So I just hit those buttons there and hit your graph. And it's going to spit out exactly what I have pasted here. Only my window's a little bit different than theirs. So mine zoomed out a little bit more and they zoom theirs in. But that's all you have to do to get the graphing piece of it is just type the function in that they give you. Yeah. So, and then you should be able to determine based off the graph what those limits are going to be. Okay, so like this next example, if they were to just give you this right here, find the limit as x goes to 2 of 1 over x minus 2 squared. You can do it algebraically, but it's a lot easier to have the graph. So I would just come in to my y equals and do 1 divided by, and just notice that you should put that x minus 2 in parentheses, otherwise it's only going to divide by x and not an x minus 2. So you got to make sure you're telling your graph to do the order of operations correctly. When you graph it, you will see exactly what we have on the screen there. So you can get that graph on your own, even if they don't provide it for you. Okay, now to find the limit as x goes to a numerical value, you have to check both sides of the function. So before you can conclude what that limit's going to be, you have to check as x goes to 2 from the left-hand side, and you have to check as x goes to 2 from the right-hand side. So you must check the two sides to make sure they match before you can conclude what the limit is as a whole. So let's check as x goes to 2 from the right-hand or from the left-hand side. So from the left-hand side, I'm following this in. And what is my graph approaching as we go to 2 from the left-hand side? Infinity. Yeah, it's approaching infinity. And it is okay to have infinity as a response for a limit. What about as x goes to 2 from the right-hand side? So following it in, it also goes to infinity. Good, so as long as these limits match each other and they're the same value, which in this case it's infinity, we can conclude that the limit as x goes to 2 must be what? Yeah, how many times we got to say infinity in the one question here? To infinity and beyond. Yep. All right, gotta channel our Buzz Lightyear here this morning. Questions with how we found that limit of infinity, but the most important part is knowing that we did have to check both sides first, right? If the sides were different, that means the limit would not exist then. Okay, how about this next one? So they do give us the table for the next one, but if we prefer the graph, we can do that as well. So if I bring up my graphing calculator just in here, and if you guys want to take a look at that on your own graphing calculator to mimic it, so sine of x divided by x. Oopsie daisy. See if I need extra parentheses in here or not. Yep, it looks like I needed my extra parentheses for this calculator. All right, we can get that graph here. Now, what do you think the limit is going to be as x goes to 0 of this function? So originally when I plug 0 in, I know that I would get 0 in the denominator of my fraction. So that's bad news. But I can use my graph to hopefully find the limit as it gets close to that. So let's go ahead and see if we can determine it based off the graph. What do you think? What do you think the limit as x goes to 0 is going to be for sine of x over x? And if this is where they bring that table in then, I think it looks like it's going to 1. Because right here, when x is 0, it looks like it's getting closer to that 1 value on the y-axis. So make sure we're looking at x approaching 0 and not necessarily x approaching 1. Sometimes our mind plays tricks on us like that. So if we bring the table up, you can see their x values are getting closer to 0, and what are those values getting closer to as we approach it from both sides. And it looks like it's a 1. So I would say the limit here of this function is equal to 1 as x goes to 0. We also knew that fact from those previous examples that we practiced with when we took a look at our properties for our limits, right? They said, looking at example 10, you know that sine of x over x as x goes to 0 equals 1. So we use that fact to kind of show our properties in that previous example on Tuesday's class. All right, questions with that? Again, this one we had to check both sides before we could say the limit itself as the whole equaled 1. All right, we've kind of reached the end of the lesson, and now we're just going to practice all of our stuff that we learned with these limits. All right, so how would you find the limit as x goes to 3 of this function right here? So you got a couple different strategies you can use. What would you do to find this limit? Knowing that there's no fractions involved with it either. Yeah, I would probably just use substitution right off the bat. And it does say find the limit by substitution as well. So that helps. But if you see something like this where there's no fraction, you can't really simplify anything, I would probably use just direct substitution. Now notice because the 3 is, or that negative sign is not inside parentheses, that's got to stay on the outside here as we simplify. What is going to be our limit as x goes to 3 of this function? Yep, -7. You can verify that graphically as well. So if I were to type in the function negative x squared plus 3x minus 7, find it, bring it back into our viewing area here. As x goes to 3, right down here is that piece of x equaling 3, right down here. Right there is that spot on that graph. You can see from the left-hand side and the right-hand side that it's approaching that 7 or -7 value on the y-axis there. So, yep, we confirm that graphically that it is going to be a -7. Okay. What about this second example? What approach would you take with the second example if you had to find the limit as x goes to -7 in this one? Yeah, anytime you see a fraction, I would try to simplify first. Yeah, so anytime you see a fractional function of some sorts, try to simplify before you use your substitution. Because my guess is if I were to use substitution right now, I probably get 0 in the denominator of my fraction and I kind of hit a dead end. And that would force me to restart and try a different tactic. So always try to simplify if you can first. So we're going to try to factor these and simplify from there. Anybody notice what that numerator is going to factor to? Yep, a +8 and a +7. What about the denominator? What is the denominator going to factor to? That's the difference of squares, right? So -7 +7. We notice we can cancel out that x plus 7 and x plus 7. We've simplified the function as far as we can go. Now we will try substitution again. So substitution hopefully should work this time and we don't get 0 in the denominator of our fraction. So substituting in, what do we get in the numerator when we simplify? And what do we get in the denominator when we simplify? A 1 over -14. Good. Now, if you were to, this is going to be the limit now, a -1/14. If you were to substitute in after you simplify and you still get 0 in the denominator of your fraction, there's a really high possibility that the limit does not exist then. I would graph to verify that it's doing two separate things from the left and the right hand side. So if you were to simplify it and then use substitution but still get 0 in the denominator, there's a really high chance that the limit will not exist then. Because after we substitute, it should take care of any problematic areas, and we can then find the limit using that substitution process. Questions with either of those examples before we look at the next slide? All right. Use the graph. So they're really nice. They actually gave us a graph here. And it says to determine the indicated limits if they exist. All right, so let's have you guys try this here. What is the limit as x goes to 1 from the left-hand side? So notice you're looking at x goes to 1, but they have that little negative exponent there. So that means you're looking at it from the left. What's going to be the limit as x goes to 1 from the left? So Tommy says 4, Isaiah says 4. I would agree. It looks like it's going to a 4. So this is the part of the graph that we're interested in. What about the limit as x goes to 1 from the right? Yeah, I would say that's 5. If we follow it from the right-hand side, it's going up to that 5. What can we conclude then about the limit as x going to 1? It does not exist. Very good. DNE. All right. Let's give you guys a little bit of time here to take a peek at these questions. And we're trying to determine if the statement is true or false by looking at the graph up above. So put either a T or an F in the space provided for each statement there. So I'll give you a moment to kind of look those over. And remember, we're trying to find, is the statement true or is the statement false? Once we have answers for all of them, we'll go through them together. All right, let's see what you guys are thinking. I'll give you a little bit more time still to kind of take a peek at that bottom row. We agree on the most part, which is good. There's just maybe, I see one right now where we kind of have altering views. So we'll definitely take a closer look at that one. Okay, so the first one here, find the limit as x goes to -2 from the right-hand side. So first of all, -2 is right here. So we got to find the graph and what that's approaching from the right-hand side. I would say that's approaching a +4, so that first one is definitely true. Good. Okay, erase my highlights. The second statement here says as x goes to 0 from the left. So here's that 0, and my graph has to approach it from the left-hand side. It looks like the limit for that would be 0. So does that equal 4 or does that equal 0? It should equal a 0. So I actually think the second statement is going to be false. So let's see who had said false here. Isaias. Nice job, Isaias. That one should be false. You're not looking for it at the exact spot. You're looking for it as it approaches. So that's the thing we've got to be on the lookout for. The limit is not what it is at that exact location, but what is it approaching as it gets closer to that. So if you had 0 here, not from the left, maybe that would be a little bit different. Okay, how about the next one? Everyone agreed with true for this one, that the limit as x goes to 0 from the left and the limit as x goes to 0 from the right is a true. Is the same. Is it true? It's the same. They equal each other. And I would say that's true. What is the limit as x goes to 0 from the left and as x goes to 0 from the right? Yeah, 0. The limit as x goes to 0 from both sides is 0. Okay, how about the next one? The limit of f of x exists as x goes to 0. So if you're looking at it from the left and the right and they're the same, yeah. So that one should be true. It should equal 0. It does exist because they go to the same number from the left and the right. Now, what's probably happening is you have an error that's occurring at that 0 point, but as you get close to it, both sides are approaching 0, so we would say that that exists, because from the left-hand side and the right-hand side, you have the same value. Okay. I'm just taking a look here. And that next one there, I want to say that that would be a true statement. But let me just double check something here. Okay, that one I do think is going to be, we'll leave that as true right now. It should be 0 for this one right here. I want to say that that is true because you're talking about the limit and maybe not the exact point at 0. So we're going to go with true there because of what it's approaching. I'm going to dig more into that because for some reason I'm second guessing myself, but for right now we're going to go with true because it is approaching the same thing from the left and the right. Okay, the last two we were in agreement there, so we should say false for both of these, but let's take a look. The limit as x goes to 2 of f of x is 4. This one's false, right? Because the left-hand side of my graph is approaching a different number than the right-hand side. So you can see that split there. So that is definitely a false for that next question. And the last one, the limit as x goes to 4 from the left. So as x goes to 4 from the left, that's this piece right here, that limit should actually be a 0, not a 4. So that one again is going to be a false because that should be approaching 0, not a positive 4. Good. So for the most part, we were good with those. Any major questions with that? I think I got one more for us to look at here still. Ooh, okay. Find the limit of the function here, where you have negative 2 over x minus 8 squared. So generally what we would try to do is simplify. Does anything simplify with that function that we have in this example? So can we simplify anything there? We can break it down, or that is, well, technically x minus 8 squared is the same thing as x minus 8 times x minus 8. But does that cancel with anything in the numerator? No. Okay, so if nothing can cancel, what's the next step generally to help us find the limit? So if we're given an actual function like this, the next step would be to try what? Graphing it, but I would actually try substitution first. I would substitute in to see if I actually get a numerical value. But when I substitute 8 in for x, what do I get in the denominator? I get a 0. Okay, that's a problem. Uh-oh, that's a problem. So my next item, because simplifying and substitution did not work, the next step is to graph, right? I'm not going to give up and say the limit doesn't exist yet. We're going to graph and try to verify it that way. All right, now the key is being able to zoom out and see what's actually happening here. All right, we can see that we got this gap here at that x equaling 8 part, which is why we had the 0 in the denominator of the fraction. But can we determine if there's a limit? So what would you do after you graph it? You can see the gap and why we got 0 in the denominator. What would you do from here to see if there's a limit? Check from the left and check from the right. Yep, so let's do just that. What is the limit as x goes to 8 from the left? So following it in from the left-hand side, what is that approaching? Negative infinity. Okay, what is the limit as x goes to 8 from the right-hand side? It's also negative infinity. So what can we say is the limit as x goes to 8 as a whole? It's got to be that negative infinity. Yeah, so that's why we don't give up if the substitution doesn't work out. It just means that it's probably not a constant value. Maybe the limit doesn't exist. That could be the case. But graphing it will then show you, is it actually going to infinity or negative infinity? Because that could also be happening. And here, we saw that it was actually going to negative infinity. So if substitution doesn't work out for us, we don't give up. We just got to try the graphing approach then. Okay, we just know that the limit's not going to be a nice constant value if there is one. We know that it's something else is occurring there. Okay, that's kind of a lot to take in because calculus it's challenging, right? And we're plugging away at it, and limits is just kind of this first step of the calculus route. So if we can really kind of understand limits now, if you have to take a calculus course in the future, hopefully you have a nice solid foundation moving in to that. All right, any questions with the limits that we looked at today? Okay, so the good news is that we have plenty of time to still practice with this 10.3 lesson. I actually don't have it assigned until next week sometime. So my plan for next week, since we only have 2 classes left, we've officially covered all the content that we need for the school year. Okay, so give the homework assignment a go. Make sure you turn 10.2 in this week, so that's definitely needed. We'll take a look at any questions you ran into from 10.3 in Tuesday's class, and then the rest of the time is yours to study for the Unit 10 test and the final exam after that. On Thursday, I will plan on going over some final exam details just to give you a heads up of how many questions there are, the times, stuff like that. So that's all I have planned for Thursday's class, but it'll be nothing full. So that one should be shortened. Even if it is due today, I won't put zeros in. I'm going to extend that to next week, Tuesday's class. So I want to make sure that you guys have plenty of time to kind of digest these concepts. Try that homework and you're still able to ask questions with it. So I'll bump back that due date till next week, Tuesday, after our class. Does that sound good? So I'll shift it on the calendar so that we can see that change. All right, awesome. So I'll do that. That's all I got for you guys today, so I'll let you guys go. Have a great rest of your week, and I'll see you Tuesday again. Bye, everyone.